Hey everyone, welcome to the Explainer. I am absolutely thrilled to take you through some truly groundbreaking research today. We're going to be diving into a fascinating paper focused on defending our web applications against a very specific, incredibly clever type of cyber threat: mutant injection attacks. Instead of relying on traditional filters, we're going to unpack a novel machine learning approach that stops these mutant, evasive threats dead in their tracks, basically by entirely changing how the AI perceives the data. Okay, let's dive into this. Here is our roadmap for today. First, we'll cover the mutant attack threat. Then, we'll look at the solution and methodology, break down the experimental results, and wrap up with the prospective benefits. So, part one, the mutant attack threat, and really the problem with traditional machine learning defenses. Look, we all know we're facing this massive, relentless menace from SQL injection and cross-site scripting, commonly known as XSS. Attackers are constantly finding new ways to manipulate databases and inject malicious scripts into trusted websites. But it brings up a huge question. How exactly are hackers sneaking these attacks past our state-of-the-art AI defenses? I mean, traditional intrusion detection systems are trained on massive datasets. They're smart. So what's going wrong here? Why are they failing? Well, attackers are leaning into something called adversarial machine learning. Basically, they take a known malicious attack and they introduce these tiny, almost invisible mutations, or mathematical perturbations, into the web traffic. It's essentially engineered noise. Now, to a human, the traffic looks exactly the same, but to an AI, it's a completely different story. If you look at how the perturbed testing data goes through the classifier, you'll see it literally tricks the neural network into labeling a malicious payload as perfectly safe. It just spits out a false label and bypasses the security filters entirely. All right, moving on to section 2, the solution and methodology, or how we actually go about building a smarter AI. Now, what's genuinely brilliant about the researchers' approach here is that they didn't try to reinvent the underlying neural network architecture. Instead, they completely changed how the AI learns and perceives the incoming data. And to do that, they borrowed a powerful concept from natural language processing called doc-to-vec. Usually, doc-to-vec is an algorithm that reads paragraphs of text, gauges the context, and converts those sentences into mathematical vectors. But the researchers cleverly realized that web traffic kind of has a language of its own, so they treated network features, things like fully qualified domain names, URL paths, and query variables, as if they were literally words in a paragraph, running them straight through doc-to-vec. By reading the network traffic like a document, doc-to-vec maps these features into a Euclidean space. What's really interesting here is how it groups similar web traffic into clusters based on context. So you can see the benign, safe traffic naturally forming one tightly packed cluster, those green dots, and the malicious traffic forms another cluster, the blue ones. The AI is basically learning the fundamental grammar of safe versus dangerous traffic. But, what happens when mutants try to blur the lines between those clusters? Well, this is where the researchers introduced a modified n-pair triplet loss. Think of this metric learning loss like a highly aggressive magnetic bouncer for our data clusters. That red node right in the center is our anchor. This bouncer violently pushes away the dissimilar mutant threats, those blue nodes on the outside, while simultaneously pulling the safe, genuine traffic, the green nodes, as close to the anchor as possible. It literally forces a massive, mathematically distinct gap between safe traffic and disguised attacks. To make this bouncer completely unstoppable, the researchers ran a robust training phase using PGD noise. And you can think of this exactly like a vaccine. First, they actually generate their own adversarial mutants using projected gradient descent, or PGD. Second, they intentionally inject that noise right into the training data. By deliberately exposing the AI to these mutated attacks during training, the model learns the boundaries of zero-day mutant attacks in advance. It inoculates the classifier, so that when a real mutant attack hits in the wild, the AI already knows exactly what it looks like. Okay, section 3, experimental results. Let's see what happens when we put this model to the test. It is time to see if this newly vaccinated model actually holds up against relentless adversarial attacks in a practical scenario. And the researchers certainly didn't mess around with small sample sizes to prove their point. They utilized the massive CIC-IDS 2018 dataset. We're talking about sheer scale here, over 1 million instances of both injection flows and legitimate traffic. And the initial results? In standard, non-adversarial settings, the model hit a staggering detection rate of over 98%. But the real test, the true measure of this model, is when things get hostile. Look at what happens when the system is subjected to heavy, targeted adversarial attacks, specifically PGD, Carlini-Wagner, and BIM attacks. The standard baselines like SVM and MLP classifiers just severely drop in effectiveness, plunging down into the 60 and 70% ranges. That means a huge chunk of attacks are slipping right through. But the crucial point here is our proposed metric learning model, the MLM, highlighted at the bottom. It maintains a highly robust 82 to 88% detection rate across the board. It just refuses to break under pressure. And this brilliantly illustrates the model's absolute superiority. This ROC curve visually tracks the performance under Carlini and Wagner mutant attacks. Check out the pink line, hugging the very top left corner. That is our MLM approach, boasting an incredible 0.996 AUC score. This visually proves, without a shadow of a doubt, that the metric learning approach absolutely crushes traditional models when facing these evasive, mutated threats. Finally, Section 4, Perspective Benefits, and why this all matters. We've navigated through some incredibly dense, albeit fascinating, computer science today, but let's tie it all back to the real world and explore exactly why this matters for you. There are massive wins here across the entire ecosystem. For organizations and enterprise decision makers, this provides a lightweight, scalable, and low-overhead defense against zero-day injections. You don't have to rip out and replace your existing neural network architectures. You just train them smarter. For students and researchers, this paper serves as a masterclass case study on how you can creatively blend natural language processing, like DocDevEc, with metric learning to solve complex cybersecurity problems. And for the broader cybersecurity community, it offers an open, generalized framework to significantly harden our AI-driven intrusion detection systems against the looming threat of adversarial machine learning. Which leaves us with this provocative final thought. Will this highly creative fusion of natural language processing and metric learning become the ultimate bouncer for our global web infrastructure? It's a fascinating prospect for sure, and a massive leap forward in keeping our data safe from invisible mutations. Anyway, thank you so much for joining me for this explainer. I really hope you found this as genuinely exciting as I did. Be sure to read the full research paper via the article link provided in the journal publication to dig into the math yourself. Keep learning, and I'll see you next time.